So, students, we are going to continue our discussions on the thermal properties, and this is lecture number 20. We have 10 more lectures to go. But before we do that, let me say something more also. So, the last lecture, what do you have finished? We finished the lecture on mechanical properties of nanomaterials, and most importantly, we talked about Hall-Page equation, the breakdown of Hall-Page equation, and other aspects related to it. And followed that, we start a new topic that's on thermal properties of nanomaterials. So, in order to provide you some recap, let me just state you that Hall-Page is basically originates from the grain boundary strengthening. Dislocations generated inside the grains are piled up at the boundaries, and this is the reason why grain boundaries can act as an obstacle to the pile up of dislocation. So, Hall-Page provides an very nice mathematical relationship between the grain size and the yield strength. This is true not only for single phase materials, but also for multi-layers and even multi-phase materials also. But at the nanoscale, Hall-Page equation breaks down. For every nanomaterial, Hall-Page equation has been found to break down basically every means metallic and ceramic crystalline materials. Hall-Page seems to break down at a grain size below a certain critical value, and that value can range from 20 to 5 or 2 nanometers. And this is something which is widely observed. The reason I have discussed about it, as the pile up of dislocation is the main reason for grain boundary strengthening. If you reduce the grain size, the pile up will vanish, and we will have a situation in which a grain can accommodate only one dislocation, and hence the pile up will not be present, and this will not lead to any further strengthening, rather it will lead to softening. Okay, this is the region where grain boundaries can lead to softening. This is something which we have discussed in the last class, right? Now, this aspect also leads to us to another important concepts like, so fine. So, that means if I decrease the grain size small and small and smaller, the strengthening due to grain boundaries is not reflected. So, now question is that if I still decrease the grain size further down to about 2 or 1 nanometers, what will happen to the material? Well, material will become completely amorphous. That is understandable, because grain boundaries are the regions of randomness compared to the grains, right? So, therefore, as you decrease the grain size farther and farther, the grain boundary area is increasing, and because of drastic increase of grain boundary area, the region of disorder or disorder regions are also increasing, and this leads to formation of amorphous structure. And this is the picture of an amorphous atomic structure where random orientations of the arrangements of the atoms leading to total disorder has been depicted. So, surprisingly, these amorphous materials are very strong, much stronger than even some of the nanomaterials. This mainly because in amorphous material, the concept of dislocation can no longer be applied. Why? Because dislocation theory or dislocation aspects in the material relies on the arrangement of atoms in the crystalline lattice. Look at the slip plane and the dislocation at this extra half plane. This whole concept is basically relies on the crystalline nature of the material. Say amorphous, where the atoms are randomly arranged, this concept cannot be applied. So, therefore, deformation behavior of amorphous material is different. although we are not going to discuss about it, but it happens because of the shear or local shear of the atoms over each other. Remember, amorphous things does not have a long in order, but it also has short in order, or what is known as SRO, right? SRO, short range order. So, these short range order clusters can move over each other, and that is how they can create, they can actually shear. And this localized shear can only be accommodated in amorphous material. But nonetheless, they have very high strength with a limited ductility, and many cases almost zero ductility. So, therefore, these materials cannot be used structurally, because they have a very low damage tolerance, low ductility. So, you cannot use them for structural application. You can use them for functional application, or maybe something like a golf head or golf bat head, actually head of a golf bat, you can do that, but not for other things. Well, as we said, so therefore, in nanocrystalline materials or in normal material, plastic deformation which happens because of dislocation motion is kind of the predominantly observed. That is the mode of deformation in these materials as compared to the amorphous materials. And dislocations are seen under TM. I am showing this picture again and again with titanium, silicon, this has been observed. Similarly, it has been observed in ceramics also. And now, the basic reasons for grain boundary strengthening is not only the grain boundary is acting as an obstacle, also grain boundary can also act as a source of dislocation. Dislocations can be generated at the grain boundaries, or maybe at the frank grid source, then they can move inside the grains, and that is how they can create a pile up. You can see that already pile up is started, 1, 2, 3, 4, pile up has started. So, one after another, just like a passenger standing in front of a railway ticket counter, same thing happens. So, this pile up model, which is have been discussing for the last 2-3 lectures, is mainly the reason for Hall-Petch equation, correct. So, central idea is dislocations are forced to pile up at the boundaries, either because of there is a barrier crossing to cross over, or because the source of dislocation must be activated in the next grain. This is something which is very important. And so, classical explanation is very simple. The stress concentration in a given grain is required to initiate initial slip in the neighboring grain, and this leads to pile up, that is shown in the last figure. Essence of the argument is that the stress is higher as the number of dislocation increases. So, stress will be much higher as the pile up, number of dislocation pile up increases, right. So, as the size goes down, number of dislocation inside the grain goes down, and at a particular grain size, you have only one dislocation can be accommodated inside the grain, and Hall-Petch concepts or Hall-Petch mechanism breaks down. That is what we discussed a lot, and this is the mathematical derivations. I will not go back into it. Okay, these are some of the things which I have shown you how the Hall-Petch breaks down in copper, nickel, or maybe in case of multi-layers also. Then we discussed something about amorphous materials. As we decrease the grain size, smaller and smaller, grain boundary area increases and the material becomes completely random amorphous. This is also observed in polymers. And so, therefore, if you make kind of strength versus density plot or strength versus ductility plot, you can do many. Some of them are there in the books also. I am not discussing all of them. You can put all the metals in nanocrystalline form very nicely. So far, so good. We are going to start a thermal properties. We have already started some part of in the last lecture. Okay, but thermal properties, I would like to reiterate something here. Thermal properties means what? Thermal properties means if you apply heat, how the changes happen, right? That is what it is. So, one of the most important characteristics of the material is the melting temperature. Okay, so, therefore, first thing we will discuss is the melting temperature of nanomaterial. Right. That is the first thing we will discuss. But that is something which is very fundamental, right? And this is very important also. Second thing we will discuss is the transport, thermal transport. and thermal transport means how heat is transported. And this happens because of phonons or electrons, correct. So, we will discuss about that also, but we will discuss this aspect of melting temperature in today's lecture. Please remember that. So, we are focusing on these two particular things. Well, there are many other things also possible, but we are not going to discuss all of them because of time constraint and because of the some fundamental concepts may be required for you to understand. That is why. So, we started with that. What is the thermodynamics description of melting of a bulk material? As you know, the basic concept is the free energy. At the melting temperature, free energy of solid and liquid must be equal. That is the fundamental concept. And below the melting temperature, solid is more stable, above liquid is more stable. So, therefore, relative disposition of these two free energy curves dictates how the free energy can be used to describe the melting phenomena in a bulk material. And we know free energy means gives free energy, it can be given as H minus Ts. And by doing a simple calculation, I showed you that gives free energy difference delta G during melting can be approximated by latent heat divided by the Tm multiplied by T minus Tm, and this can be written again latent heat divided by Tm multiplied by delta T, where delta T is always considered as the supercooling, right. How much lower the melting temperature you can do the melting. Okay. So, this is how we can actually one can actually derive the delta G of melting during melting, the amount of piece free energy because of melting. So, as you can clearly see, this difference is, or delta G is basically proportional to delta T or T minus Tm. Why? Because latent heat and Tm are constant for a particular material. Remember, we are discussing about bulk, we are not discussing about for a particular material, we are not discussing about nano. So, this is something which is very, very important for you to understand. This derivation is there in any thermodynamics books you can do. But what happens when you have nanomaterials, right? That is something which you should know very well. So, as you know, so therefore, for nanomaterials we have written already many times delta T total can be written as delta T bulk plus delta G surface, right, because nanomaterials have high surface to volume ratio, and therefore, delta G bulk as we have written above then can be written as L T minus T minus T m divided by T m, correct. Is it correct or wrong? Let me correct it. No, it is T m minus T, it is not T minus T m. So, it is T m minus T. So, I should not make a mistake, right. So, it is T m minus T into, you have to multiply a volume, because this is the volume free energy. So, if you want to know total free energy, you have to multiply the volume of the liquid, correct. This part is the free energy change because of transformation from solid to liquid per unit volume. So, if you want to know what is the total free energy change, you need to multiply by volume of liquid. So, therefore, L is a latent heat, Tm is the melting temperature of the bulk material, and T is the melting point of the vessel, T is the any temperature. And in the ASBIS book, it has been written as the melting temperature of extended system, that when surface effects are there. So, that is something which we can easily, we have derived in the last class and we can use it. What about delta G surface? Delta G surface is equal to what? That is equal to, you know that is gamma and delta A. right. Gamma is the specific surface energy, and gamma is the specific surface energy, and delta is a change in the area, right. That is something which is, or basically delta is nothing but change in area. Right. So, evidently at the melting temperature something must be happening, and that you should know, then only you can calculate delta A. So, that means to know change of area we must know how melting happens for a nanoparticle, right. Then only we can come back to it and then calculate it. So, let us see that how it happens. So, these are the few experimental things. Okay. Just look at the structures. This is a nanoparticle, something like about, say, dimension is about 10 nanometers or so, and it has been heated up. Because of heating, it started melting from here, you can see. How do you know it has melting happened? Well, liquid has an amorphous structure. Obviously, you can see all these things under transmission electron microscope. You cannot see these particles, things happening in other microscopes. So, you have something happening at the surface here. The contrast, which is mainly because of the crystallinity of the material, is lost, and that is why you can see there is an amorphous like picture. There is a random arrangement of atoms, and slowly the liquid, the things start melting down. Slowly the things will start melting down, you can see here, and this part is slowly decreasing, is molten, okay. Or finally everything is molten after 130 minutes or so. So, that means liquid layer forms on the surface, that part is clear, okay. And then it grows inside. That is understandable, because melting requires formation of the liquid. Liquid cannot form inside the particle. It can form, there are some peculiar cases, but in general liquid can only form on the surface of the particle, because surface acts as a nucleating agent for the liquid, right. So, this is something which is very, very widely observed in many particles. Even you can look at this particle, which is indium, okay, and once you start heating up, it will melt nicely, okay. So, I will show you some pictures later, but very clear that the melting happens in a surface kind of things. Surface starts melting first. So, the model which people normally use is like this. This is there from Ashby's book, Michael Ashby, and let us assume a solid particle of something like a radius of r, correct, radius of r, and so this particle started melting down. So, when it started melting down, it forms a thin layer of liquid at the surface. You might be thinking in the picture liquid was forming from one side, but remember in TM you see only the projection of the image, you do not see the whole solid particle. So, whether liquid has formed all throughout the surface or not, it cannot be completely confirmed, but we can always assume that liquid will likely to form on the surface evenly on the particle. So, suppose this liquid forms, and because this liquid has formed, so this is the R, and this thing become R minus T. Am I right? So, now we can do something, we can very easily understand, and this is some kind of particles on which if liquid forms, you cannot apply, use basically assume spherical assumptions. You have to know the particular shape and calculate it. So, my idea is to show that the actual life is more complicated than whatever we do to understand things, but nonetheless to keep it simple and nice, let us assume the particle is spherical. Let us not assume the particle has facets, and then you have to calculate area of the facets, and other complication comes into picture, which facets will melt first or not. Let us assume a spherical particle with radius of r. When it starts melting, it forms a liquid layer on the surface of the particle, and liquid layer has a specific thickness T. Okay. So, now obviously, delta A, or rather I will write down delta G is gamma delta A, right. So, these can be expanded, then what? AL gamma L. Okay. What is AL gamma L? Okay, AL is the area of the liquid which is formed and the intersurface energy of the liquid. See, the difference is this. Compared to configuration A, if you compare them, what is the difference? In the configuration A, you have only AS gamma S, because this is a complete solid. So, gamma is the surface energy of the solid, and if you know the area of the solid, then you know what is the total surface energy. But here you have AL gamma L. Why? Because liquid has formed on the surface. Liquid has formed a surface of the solid and it has covered the solid. So, therefore, the new surface which has formed is a liquid, plus you have formed a surface ASL gamma SL, right. This is the surface between solid and liquid. So, formation of liquid leads to two kinds of surface formation. One, liquid with the atmosphere, another one is liquid with the particle. And each of these surfaces has different surface energies. So, that is why if I have to consider gamma and delta A properly, so I should write down ASL gamma SL minus AS gamma S. This is the difference. Correct. This is the main difference between these two situations. That part should be clear. Okay, am I very clear? If you are not understanding properly, you can always ask me a question later on when the discussion happens. So, this is something which is very typical even in nucleation of soil also. Those of you who study metallurgy, they know that for heterogeneous nucleation of solids from the liquid, we use such a kind of expression also. So, AL into gamma L is this surface energy means surface energy of the liquid, ASL into gamma SL is this surface energy, and this one is this surface energy. So, new configuration minus the old configuration, that is what gives you the change of the G gamma. So, now I can go back. So, therefore, G total is L Tm minus T, sorry, Tm minus T, not T naught, must not make a mistake here, divided by T naught at Tm multiplied by VL plus AL gamma L, ASL gamma SL plus what? Plus, sorry, minus, not plus, minus AS gamma S. That is what we did. This is the total free energy of the system. Now, if you want to know the equilibrium between these because of melting, then you should make sure the del of G total as a function of the thickness must be 0, because you are creating a liquid layer on a solid. This liquid layer on a solid is thickness of that is a variable. So, at any temperature, how much will be this thickness, that will depends upon the equilibrium between the solid and the liquid. So, that is why if you apply this minimization principle of the delta G with respect to thickness T, this is the thickness T, okay, then you can get a relationship between melting temperature and something, right. That is what you have understood. Now, I go back. Okay. So, this is again to show you how the melting actually happens. You see, as this is called homogeneous melting, which is very rare, rarest of rare, rarely has been observed, or you can say it is never observed. This is something heterogeneous nucleation of liquid and growth. This is something which happens very regularly. Okay. You can see solid the liquid layer and liquid layer grows and melts. Okay. Or you can also have liquid skin melting, That means you have a very thin layer formation, a thin layer slowly grows, and whatever the situation, this liquid layer grows inside every time and melts. This is the model which is widely used in the literature, and this is acceptable. That is what we did. Okay, again I am showing you these aspects. So now, I will write down again the whole thing. G total is L into T m minus T divided by T m into V L plus A L gamma L A gamma S L gamma S L minus A S gamma S. Am I clear? So now how do you calculate AL, ASL and AS? How do you calculate that? Let us do that. Okay, again, so this is the advantage of using. So AS is basically coming from this is 4 pi r square, surface area of this particle, right? What about AL here? Again, this is r and this is r minus t. So AL is what? AL is again 4 pi r square, right? Because it is a liquid, liquid has a radius of r. So what about ASL? ASL is this surface area. So that is nothing but 4 pi r minus t whole square. Am I clear? Correct. So AL and AS are same, ASL is different, correct? So what do? You plug in all the values and this remains constant, Tm minus T by Tm into Bl. And what is the volume of the liquid? Volume of this liquid is what? Don't know, right? Obviously you should know it. Volume of the liquid is in the annulus place. No, that is not the volume we are considering. Volume, when the whole thing is molten, then only the whole transformation is complete. So therefore that volume is 4/3 pi r cube. Okay. So we can write down that. Four-thirds pi r cube. AL is 4, mistake. AL is 4 pi r square into gamma L, and this is 4 pi r minus t square gamma S L minus 4 pi r square gamma S. Okay, you understood, right? You clearly see 4 phi can easily be taken out from that. Okay. Delta G total by 4 pi is become L T minus Tm minus T by Tm r cube by 3 plus r square gamma S L plus r minus t square gamma S L minus r square into gamma S. Am I clear? So now what do? Okay. I think we are making here a mistake. That is very clear. They are not considering this liquid. So I am sorry, I made a wrong assumptions. So this should be this liquid layer, which is nothing but. So if you see, this is the difference between the volume 4/3 pi r cube minus 4/3 pi r minus t cube, right? So that's become that you can easily calculate. Okay, so 4/3 pi r cube minus 4/3 pi r cube 3 r square t plus 3 r t square minus t cube, right? So that can be easily this one get cancelled, 4 pi third cube. So what remaining is this 4 pi by 3 into 3 r squared t, right. We can ignore all of these terms. 4 by 3 pi into 3 r t square. T q term anyway you can ignore. So 3 get cancelled, 3 get cancelled. It's become 4 pi r square t plus t square r. Am I clear? So that's what we should use. We should not use this. There's a mistake we have done. So let us correct it. We'll write it here, VL. The next step we are going to write it L minus Tm minus T by Tm into, what is that? 4 pi r square t plus t square r minus, it is not plus, I think this is minus, yes. So 4 pi r square t minus t square r plus r square gamma L minus gamma S, okay, plus r minus t square gamma SL, sorry, gamma SL. So now if you, this is what is delta G total by 4 pi. So now if you do a derivative of that with respect to thing, with respect to time, that thickness, what do you get? It will become L Tm minus T by Tm, 4 pi remains, so it's become r square, and then it's become twice r t, right, twice r t. This is 0 actually, because there is no t term here, this becomes 0, and then you can write down r square nothing, twice minus twice gamma, so twice 2t and 2r gamma SL, right, correct. So you can write down these aspects very easily. So when at the limit t goes to 0, you will find this relationship valid, that is L Tm minus T naught T by Tm is equal to twice gamma SL, twice gamma SL by r minus t. You will find that both the cases you are getting r minus t, correct, both the cases. Okay, let me do it before I derive it. So let me erase it up. You guys may be thinking bad, so let us do that. So what you can do? You can write down this expression in a nice manner. L minus L to Tm minus T by Tm, okay. So this is 4 pi r common, r minus 2t, so r minus 2t plus 2 minus 2 r minus t gamma SL, right. So this is something which is the actual expression. So once you do this analysis properly, that means once you assume delta G by del T going to 0 as t tends to 0, okay, t tends to 0, not infinity, t tends to 0, okay. Then what do you get? You will get this expression L T m minus T by Tm is equal to twice gamma SL by r minus t, okay. So if we assume t tends to 0, then it's become L Tm minus T by Tm is equal to twice gamma SL by r, right, or rather I can write down Tm nano, that is equal to T, okay, we are making T as a Tm minus nano, that has become Tm 1 minus twice gamma SL by L0 into R. So this is the relationships which can be easily obtained by using this model. So therefore melting temperature of any nanoparticle is given by this expression. So it's getting reduced by a factor twice gamma SL by L0 multiplied by R. So, as you decrease the particle size, the effect of R becomes stronger. This factor increases substantially, because you know gamma SL for a particular system is constant, L0 of the particular system is constant. So, therefore, the factor which plays a role is the melting the R or radius of the particle. Some part of this we discussed already in some lectures before, but this is the thermodynamic model which can be increased. So, as you clearly see, this twice gamma SL by R, this term is associated with the increase in the internal pressure resulting from the increase in the curvature of the particle. That is we have seen. This term, okay, twice gamma SL by R is basically associated with increase of the pressure because of increase in the curvature of the particle, or decreasing particle size. So, variables like gamma SL, L0, R are all positive quantity. This means that upper melting temperature of a spherical particle decreases with decrease in the particle size. And I will show you some of these experimental results. But this is for the gold, pure gold. See, this is the bulk melting temperature, okay, 900 something, and then as you decrease the particle size, this is how the trend follows. So, about 40 nanometers or so, decrease is not much, but as it goes down to 10 or 5 nanometers, decrease is substantial, almost like a 200 degrees Celsius, okay, almost 150 to 200 Celsius decrease. This is true for lead, this is true for copper, bismuth and silicon. Obviously, there is no experimental results are put up on for the copper, bismuth and silicon, but trends should be same, and that is what is observed in real picture. So, that means the experimentations validates this model which I just now discussed. So, nanoparticles will lead to decrease in the melting temperature. That is what is very clear, and these results also show that. Remember, these discussions are only for free nanoparticles which has nothing on the surface. Okay. I know I am making a big statement here, because all this material nanoparticle may have oxide on the surface, that is fine, but we are talking about nanoparticle coated with something, embedded in some matrix, that is a completely different situation. So, I hope you have understood this model, and this calculation I would like you to do yourself and confirm. So, whenever we come back, we will discuss further. Well, so that is why we are going to change, and next 10 minutes or so, we are going to discuss something different. So, that discussion was mainly for the nanoparticles which are free, which are not embedded, which are not coated. But I have shown you some pictures earlier, and in fact, the left hand side picture, you see this is the left hand side picture, and in this picture you can see nanoparticles are dispersed in a matrix. Okay, this is the matrix, right? And here this is taken from Nicholson and Thomas and Nutting. This is basically aluminum matrix, and this is the precipitates. So, that means what? Here the precipitates are embedded in a matrix. So, what will happen to these particles? Will they follow the same model? Obviously not, because here the particles are embedded in a matrix. So, their behavior depends upon the matrix particle interface. Remember, in the earlier model here, what is the model is using? We are using a free particle, liquid is forming on the surface. So, here the particle is not free, they are embedded. So, how the liquid will form between the particle and the matrix, that is what will dictate how the melting will happen. So, let us talk a little bit about that. Will this nanoparticle melt as usual below the melting temperature of the bulk or not? Well, to answer this question, we need to consider the fact that surface of the nanoparticle is in contact with the matrix instead of being exposed to the surrounding atmosphere, like in the earlier case. Surface of the nanoparticle is covered or in contact with the matrix. Therefore, the interfacial area and interfacial energy per unit area gamma SL, which we used, must be energetically balanced by Young's theorem. What is that? What is that Young's theorem? This is what it is. So, if you have a particle sitting on a substrate, and there will be a contact angle between the particle and the substrate, and this is where the surface energies are balanced. This is the point here, you see. This is again taken from book of Michael Ashby and others, and you can write down very easily gamma Lm is equal to gamma LM equal to what? You can balance that. Can I do that? You should be able to do that. Gamma LM is equal to gamma SM plus the cos theta of this term, that is gamma SL cos of theta, right. So, we can write down cos of theta, which is the contact angle, cosine of contact angle, is a gamma LM minus gamma SM by gamma SL. This is what is known as, this top equation is known as Young-Dupré equation. Okay. This is again Thomas Young, same guy who discovered double slit experiment of diffraction. Okay. So, this is something which is very clear. So, that means what? The gamma SL is now replaced or must be energetically balanced by the other two surface energies. Remember, nanoparticle is embedded in a matrix, right? That is what we showed. Nanoparticle is embedded in a matrix. So, therefore, matrix nanoparticle energies must come into picture, and that we must not forget to include, correct. So, therefore, gamma LM, here gamma LM is what? Gamma LM is the liquid matrix interfacial energy when it is molten, and gamma SM is the solid matrix interfacial energy per unit area, and theta is the what is known as a deviating angle. By arranging the equation, and if we assume theta to be 90 degrees, that is what is shown here, it can be shown here there very easily when theta is 90 degrees, when gamma SM is greater than gamma LM, melting temperature nanoparticle should be, melting temperature of nanoparticle should be less than the melting temperature of the bulk, correct. Cos theta, when theta is 90 degree, cos theta is what? 0, cos 90 is 0. So, therefore, the sign will depend upon SM and LM, correct. The energy sign will depend upon SM and LM very clearly. So, therefore, melting temperature in embedded particle, but when gamma SM is less than gamma LM, the T nano will be greater than Tm bulk. So, you have two situations here, you can clearly see, not one. In one case, you can have the similar situation like in the earlier, melting temperature nanoparticle will go down, in the other case melting temperature can increase compared to bulk. That is very interesting, right. So, you can melt a particle nano size at a temperature higher than the bulk melting temperature. I know some of these things we also do research in our labs. So, this situation letter 1, now situation number 2, situation 2 is this one is known as superheating. Why it is called superheating? Because you are increasing the melting temperature beyond the melting temperature of the bulk. Okay. And see this, this mainly because of the interface between the matrix and the nanoparticle. Okay. So, you can see a SM is what? SM is matrix particle. So, matrix particle interfacial energy is lower than the liquid matrix interfacial energy. So, solid and particle, solid particle and the matrix interfacial energy is less than the interfacial energy between the liquid and the matrix. So, liquid will not nucleate, because liquid has there is a gain in keeping the solid in the solid form, because energy is not gained by doing the process. If I make the particle liquid, okay, we are not gaining any part of the energy, because the system is saying that by keeping in solid form, energy of the system will remain lower. So, that is why particle will try to remain solid as high as possible temperatures, and that is why the particle will get superheated. This is nicely described in Asby's book, and whatever I said, everything of that is written nicely in the Asby's book, except the derivation which is supposed to do as a part of assignments. So, this derivation which I did, I think this is should be your assignment. And all of you need to submit the assignments. This is lecture number 20. So, in lecture 21, before I upload the lecture number 21, you must come up solution of the assignment, then and you will be graded for that also. Okay, so that's something we discussed. So there are a lot of examples of these embedded nanoparticles. Here I am showing some of these. Okay, this you can see that some of the particles are in the matrix or something. Okay, in fact, this is very common in this system. So let me stop here. So we have discussed quite a bit in this class about the melting temperature, depression, and what are the two different situations we discussed. One is the free, other is the embedded nanoparticles, and I described to you different kinds of situations in case of embedded nanoparticles. So in the next lecture, we are going to talk about thermal transport. Thermal transport, how thermal transport happens, and how it can be dealt with mathematically. Thank you.